Hello there, friends. We are going to talk about rectilinear motion today, and that's velocity and motion along a line. And so one of the things that you need to know about rectilinear motion is its motion along a line. So if I take my pi, which is super cute, and I move it up and down, that's rectilinear motion. If I move it left and right, that's rectilinear motion. But if I toss it, that's projectile motion. That's not what we're talking about here. So we're saying if I toss it straight up and straight down or drive it left and right, that is rectilinear motion. And so there's some vocabulary that you need to know. And some of those I'm just going to go through quickly. Position is where you are. Displacement is how much where you are changed. So your displacement is your net change in position. Average velocity, that's your change in position divided by your change in time, your displacement over time. And so your average velocity is like if I go from Rochester to Boston, it's about 300 miles. And if I drive to Boston in 6 hours, 300 divided by 6 is 50 miles per hour. That would be my average velocity. Instantaneous velocity, however, is if while I'm driving and I'm on 90 and I look down at my speedometer and my speedometer says I'm going, say, 67 miles per hour, that number is my instantaneous velocity. Now, we can contrast that instantaneous velocity with speed because instantaneous velocity can be both positive and negative. Average velocity can be both positive and negative depending on direction. If I drive from Rochester to Boston and I'm looking at a map where north is up, I'm driving to the right, I could consider me driving to Boston positive velocity, but me driving home from Boston as a negative velocity. Speed, though, is what my speedometer is going to show. That's always a positive number. So when I look down at my speedometer and it says 55, I'm going 55 miles per hour in speed. I might also be going 55 in velocity, but it depends on what direction I'm going. And then last but not least is acceleration. Acceleration is the rate of change of your velocity, not of your speed, of your velocity. Okay, so I'm just going to give you some notation right now so that you're aware of it. And our position you will see written as S of t, or sometimes X of t, or sometimes H of t. That's going to be your position. We use H if we're talking about vertical motion because we consider that height. X of t is if I'm driving left and right. It's like I'm driving along the X axis, so we use X of t. And S, just sometimes just for fun. Displacement is the net change in your position. So that's going to be X of t2 minus X of t1. Okay, and remember displacement is your change in position. Okay, I could have used X or H or S, doesn't matter. Average velocity is displacement, oops, forgot an either, divided by my change in time. So that's going to be X of t2 minus X of t1 over t2 minus t1. Okay, average velocity is the change in your distance divided by time. Average velocity has nothing to do with velocity. It's just displacement over time. Okay? Now, when we get to instantaneous velocity, here's where the calculus comes. Instantaneous velocity is going to be the derivative of position. So instantaneous velocity is going to be like X prime of t, or H prime of t, and we usually call it V of t. Okay? Speed. Speed is always positive, except when we're stopped, and speed is 0. Speed is the absolute value of velocity. Okay? Speed is never negative. Whereas instantaneous velocity and average velocity can be positive or negative or 0. Speed is only 0 and positives. And acceleration is the rate of change of your velocity. So acceleration is the derivative of velocity. So that is going to be the second derivative of position, which is the first derivative of velocity, my face is in the way, which we usually just simplify down to a of t. Now, if you're thinking, can I just write a of t? Not until you link it to x double prime or v prime. You have to link it back to what you started with. Once you link it and you say, oh, I'm going to call x double prime a of t, then you can just start using a however much you want. Average acceleration is kind of like average velocity. Average acceleration is the change in velocity over the change in time. Just like average velocity was the change of displacement over time, average acceleration is just delta velocity over delta time, which would be like vt2 minus vd1 over t2 minus t1. Okay? Now, if you're thinking, oh my gosh, I have to memorize all this, I mean, yeah, but we're going to use it so often, it's just going to stick in your brain anyway. The one, if you're thinking, what should I absolutely memorize? I would tell you, you absolutely need to memorize that average velocity actually has nothing to do with velocity. It has to do with position and time. Okay? Now, I'm kind of lying. Average velocity does have something to do with velocity, but that comes later. So for right now, average velocity is displacement over time. All right, so let's do some stuff. A thrown basketball's height can be calculated using the equation h of t equals 5 plus 40t minus 16t squared. Now, this is the part of the course, finally, where we're going to get a chance to use the calculator. So if you have a calculator nearby, great, grab it. If you don't have a calculator nearby, it's fine. We'll work one out together, okay? A thrown basketball's height can be calculated using the equation there. Write an equation for the basketball's velocity. Well, velocity is the derivative of position, and position can be our height. So h prime of t is going to be what we call v of t, and we are going to take the derivative of the side equation. And that's going to be 40 minus 32t. Okay. Write an equation for the basketball's speed. Well, speed is the absolute value of velocity. We often don't give it a letter, so I'm just going to write it as speed equals the absolute value of velocity, which is the absolute value of 40 minus 32t. Write an equation for the basketball's acceleration. Well, acceleration is the second derivative of position, which is the first derivative of velocity. And the derivative of 40 minus 32t is negative 32. And so now I have my equations, and then it says what's the displacement of the basketball. So displacement is your change in position. So I want my change in position from t equals 1 to t equals 2. So I need my height at 2 minus my height at 1, which is going to be 5 plus 40 times 2 minus 60 times 2 squared minus 5 plus 40 times 1 minus 16 times 1 squared. And you are allowed to use a calculator. I am going to pull up some Desmos here and get this rolling. But yeah, it's calculator time. Awesome. So I had 5 plus 40 times 2 minus 16 times 2 squared minus 5 plus 40 times 1 minus 16 times 1 squared, and I get negative 8. Okay, cool. My displacement is negative 8. Now, what does that mean? Let's talk about that for a minute. And let's talk about maybe like some units. So it says a thrown basketball's height. I should have said in feet. Can be calculated using this equation where t is in seconds. So let me come back and give you some more information right now. So if I'm measuring my basketball in feet and over time of seconds, if my displacement is negative 8, that's a change in position, so that is negative 8 feet, and that means from second number 1 to second number 2, the net change in the height of that ball was negative 8 feet, aka the ball is 8 feet lower at t equals 2, than it was at t equals 1. That's it. All right, what is the average velocity of the basketball on the time interval from 1 to 2? Well, average velocity is displacement over my change in time. So that's going to be -8 over my change in time from 1 to 2, which is 2 minus 1, which is 1. And so that's going to be -8. Now let's talk about units here. This is displacement, which is measured in feet, and time, which is measured in seconds. So my average velocity is in feet per second. So on average, over that window, the average velocity of the ball was -8 feet per second. Okay, so now let's talk a little bit more about some of these signs and meanings, positives and negatives, and things like that. In general, these signs make exactly as much sense as you want them to make, so it's not going to be really hard for you to memorize these sign things, but you still need to know. When an object is to the right or above some kind of origin, whether that origin be like sea level or the actual origin or some kind of reference point, if an object is to the right or above some kind of reference point, you have positive position, whereas if you're to the left or below, you have negative position. Okay? When an object is moving left and right, the movement assigns a sign to velocity. So if we are moving to the right, we have positive velocity. If we are moving to the left, we have negative velocity. Okay? Same with if I'm moving up, positive, moving down, negative velocity. When velocity increases, okay, so velocity increasing, whether that velocity is positive or negative, I do not care, but if the value of velocity is increasing, then acceleration is positive, and it is positive for a calculus reason. That calculus reason meaning, if my velocity is increasing, then the derivative of velocity, aka the slope of velocity, would be positive, because if I have a function that's increasing, it has positive slope. And then if my velocity decreases, I have negative acceleration. Okay? So acceleration is positive when velocity is increasing. Acceleration is negative when velocity is decreasing. Okay? When the graph of velocity moves away from the x-axis. So let's think about this one for a minute. If I graph velocity, it's right there. And now it says when the graph of velocity moves away from the x-axis, what happens to speed? Well, speed is the absolute value of velocity. So if I want to take this graph here, and I want to change it from a velocity graph to a speed graph, all I have to do is reflect everything that's below the x-axis to above the x-axis. So this is velocity that's already positive, so the speed is positive. This stuff down on the bottom where velocity is negative is going to reflect up. And so now this pink curve that I just made, that's the speed curve. Okay, well, what does that mean when the graph of velocity moves away from the x-axis? So let's see, when is that happening? Well, my velocity is moving away from the x-axis right here. Well, if the velocity is going from positive to more positive, then my speed is going from positive to more positive. My speed is increasing. That works the same way below the x-axis. When my velocity right here is moving away from the x-axis, my velocity is going from a slightly negative velocity to a more negative velocity. Well, if velocity goes from being negative to more negative, then speed goes from being positive to more positive. The speed is increasing. Okay, I'm really trying to drive this home, but basically, if velocity moves away from the x-axis, speed is increasing. And if velocity moves toward the x-axis, that means velocity is getting closer to zero, so my speed decreases. Okay. So when we talk about speed, something's speed increases when the speed graph increases. I mean, duh. All right, speed increases when speed increases. It's a tautology. Well, of course that makes sense. But there's more to it than that. So there are actually 3 ways to figure out when speed increases. 1, if you have a speed graph, speed increases when speed increases. Again, duh. 2, speed increases when a velocity graph moves away from the x-axis. Yeah, I already said that too. But there's a 3rd way. Speed also increases if you know that velocity and acceleration have the same sign. Okay, so let's think that one through. If velocity and acceleration have the same sign, that means velocity is positive and increasing, because if velocity is increasing, acceleration is positive. So if velocity is positive and increasing, that would mean velocity is positive and acceleration is positive. Got me? Or if velocity looks like this, but it's below the x-axis, if velocity is negative and decreasing, that means my velocity is negative and the slope of the velocity is negative, which means a velocity and acceleration would have the same sign again. Okay, and so for this, I'm going to use Travis the tardigrade. This is Travis, okay? He's a tardigrade, he's awesome. So here's Travis the tardigrade. Travis the tardigrade would speed up when I drop him, right? As I drop Travis, his speed is increasing. Well, Travis, though, is moving down, so he has negative velocity. Travis's velocity is negative and getting more negative. If you know anything about physics, Travis's velocity is negative and gravity is a negative acceleration, negative 9.8 meters per second squared or negative 32 feet per second squared. So when Travis has negative velocity and is being affected by negative acceleration of gravity, that's why his speed increases. So you can speed up when you have negative velocity and it gets more negative, or if you have positive velocity and it gets more positive. Okay, then last but not least, a speed decreases or something slows down when the speed graph decreases, which would be when the velocity graph moves toward the x-axis, or when, what was I going to say, when velocity and acceleration have different signs. Okay. So this was a whole bunch of like notes and vocabulary and everything like that. I am going to stop there for this chunk of the video. We are not yet done with lesson 1, but this is where I'm going to stop this video so that you can pause and take a break. So have a wonderful rest of your afternoon, and maybe it's still going to include more calculus. I hope so. Bye.